Okay, what is this plot? This is looking at the difference between, this is simulating a toss of a coin, 50% chance of heads. And it's looking at the difference between the observed fraction of heads and the probability of heads. In this case, it's 800 trials. So what tends to happen as the number of trials gets bigger and bigger is that the difference settles down to 0. So initially, for a small number of trials, there's a pretty good chance that the theoretical chance of success and the empirical rate of success is going to differ by a lot. But as the number of trials gets bigger and bigger and bigger, the probability that they differ by very much gets smaller and smaller. Let's do another. Okay, so now here's the story for a coin that has an 11.6% chance of heads, and we're taking the difference between the observed number of the observed percentage of heads and 11.6%, the theoretical probability of heads. And again, it wanders around a while, but eventually this kind of settles down and gets very close to 0. Okay, so this is the difference between the percentage of heads and the probability of heads for this biased coin that has an 11.6% chance of heads. What happens if instead of looking at the difference between the percentage and 11.6, we look at the difference between the number of successes and 11.6% of the number of trials? Okay. Law of large numbers doesn't say that that gets small. All right, so I just toggled this. So now instead of plotting the difference between the percentage of successes and 11.6% of the number of trials, sorry, and 11.6%, I'm plotting the difference between the number of successes and 11.6% of the number of trials. This tends to actually grow the more trials you have. So the difference between the number of successes and the probability times the number of trials tends to get big. The difference between the fraction of successes and the probability of success tends to get small. Okay? How can those things simultaneously be true? Okay, here it is for an example for a fair coin. So it starts off, this is the difference between the number of successes and 50% of the number of trials. And it just wanders off. But if we look at the difference between the percentage of successes and 50%, it tends to get small. What's the relationship between the number of successes and the percentage of successes? Okay, so the number of successes tends to grow, but the probability of success times the number of trials also tends to grow. So we're comparing two things that are growing. But just mathematically, percentage of successes right? So that's the relationship between percentage of successes and number of successes, right? They're related through the number of trials. Okay, so suppose if the number of success, if the difference between the number of successes and p times the number of trials grows at the rate of n, the number of trials, or faster, then the percentage of successes wouldn't get closer to the percentage, to the probability of success. But if the number of successes, the difference between the number of successes and p times the number of trials grows slower than the number of trials, when you divide by the number of trials, that difference is going to get closer and closer to 0. So in fact, what happens is that the difference between the number of successes and the number of trials times the probability of success tends to grow like the square root of the number of trials. Okay, it grows slower than the number of trials. So when you divide it by the number of trials, it ends up getting smaller and smaller. So even though it grows slower than the number of trials. When you divide by the number of trials, the result gets smaller and smaller. Does this make sense to people? All right. If I have something that looks like a constant times the square root of n, and I divide that by n, what happens is n gets big. This is constant over the square root of n. This gets small as n gets big. Okay? So even though this is growing, it's not growing as quickly as that is. And as a result, when you divide it by n, it gets smaller and smaller. That's what's going on here. The difference between the number of successes and 50% times the number of trials tends to grow. It tends to grow at the rate of the square root of n. But when you divide it by n to look at the difference between the fraction of successes and the probability of success, that tends to shrink at the rate of the square root of n.